We have already learned about the principle of superposition and the wave equation. In this session we would study systems capable of producing sound waves, which are also known as acoustic waves. This topic is not altogether new, and I know that you have studied some aspects of this already at the high school level. There are three main points that I wish to emphasize at the outset. Let us discuss these 3 points one by one. Point 1, that the sound waves propagated by local variations in density. Imagine that a parcel of air near a vibrating source becomes compressed. Its density rises above the threshold value. The parcel would want to return to the uncompressed state as the medium is elastic, and in that attempt compresses an adjacent layer. The process can't use and forms a harmonically varying density field known as the sound wave. Point number 2 is that the waves propagate in a fluid. An ideal fluid does not support shearing forces, and therefore, sound waves are not transverse in such a medium. On the other hand, transverse elastic waves do form in a solid medium, and they propagate in a direction perpendicular to the direction of propagation of the wave. Point number 3 is that sound waves can only form when the mean free path of molecular collisions are less than the wavelength of the sound wave. In air at standard temperature and pressure, the mean free path is of the order of 68 nanometers. This is so because the large wavelength of sound waves do not allow the molecules to effectively see the changes in the medium that would occur over the length of a wavelength, else they would have neutralized these changes automatically by their collisional exchange of energy among themselves and brought back the medium to its pre-existing local equilibrium conditions. Here pre-existing means before the passage of the wave. This condition is illustrated through a problem in the next screen. This table, taken from Wikipedia, describes progressively higher vacuums. Given the audible range of sound 20 Hz to 20 kHz, one can calculate the wavelength from the relation C equals EFF lambda, where the sound speed is 343 meter per second in STP. Note that the value of the sound speed depends on the ratio of the pressure and density, and so it is held constant as long as the temperature of the medium is held constant. We find that the wavelengths vary from 17 mm to 17 m, and sound waves cannot be sustained from low vacuum onwards. The standard atmospheric pressure is usually stated in the unit of bars, where 1 bar is 10 to the power 5 pascals, the SI unit of pressure. The standard atmospheric pressure is about a bar, or more accurately, 0.987 bar. Pressure levels are often measured in units of decibels. A decibel is 20 times the logarithmic ratio of the prevailing pressure to a standard reference pressure. The reference pressure is 10⁻⁻⁷ bars, small in any standard. The standard atmospheric pressure is about a crore times larger than this. Decibels are good for measuring quantities where equal ratios rather than equal magnitudes are perceived as equal changes. This is true for many natural detectors like the ear, where musical notes which differ in integral ratios of frequency are perceived to be the same. Instruments based on this principle are known as logarithmic detectors. Logarithmic detectors also have the advantage of accommodating a large range of the scale variable. The very small reference value for pressure levels indicate that very small changes in the sound pressure levels are behind the phenomena of sound propagation. The accompanying problem asks you to determine the change in the pressure levels when a sound wave of moderate amplitude passes through the media. Setting the dB to 60, we solve for the pressure. It is 10⁻⁻⁴ bar, so the change in the pressure is only 1/10,000th of the original level of 1 bar. Since the pressure changes very little when a sound wave passes through a medium, it makes sense to talk about quantities in excess, which we define next. The excess pressure is the deviation of the pressure level from the ambient, unperturbed level. The total pressure, by the same token, is the sum of the ambient pressure and the excess pressure. The same goes for the density. Note that these excess quantities are written with small letters with the suffix e. In some books excess quantities are written as delta P, delta rho, etc. The pressure and density fluctuations which would occur in the medium are not uncorrelated, they are connected by an equation of state, henceforth called an EOS. The EOS is a relationship between the pressure and the density of the medium. For our purpose, the equation of states will appear in their polytropic form, in which the pressure would be proportional to a power of the density. The power appearing in the exponent of the density goes by the name of polytropic index. The degrees of freedom is related to the polytropic index gamma by the relation gamma equals 1 plus 1 by n. Two examples are important: the isothermal viewed as a polytro of index 1 and the adiabat which is naturally cast in the form of a polytro with index equal to the adiabatic index. The equation of state allows us to relate the excess pressure to the excess density. We express the total pressure as a function of the total density. The density is then expanded in a Taylor series to first order about the ambient density. After cancellation of the ambient terms from both sides, we see that the excess pressure is in fact proportional to the excess density, with the proportionality constant being the value of the derivative of the pressure density function computed at the prevailing density. With the definition of the excess quantities, knowledge of the polytropic form of the EOS, and the awareness that the excess pressure being proportional to the excess density, we are all set for obtaining the wave equation that describes acoustic waves. Consider two horizontally separated points in an unbounded, one-dimensional medium. Call them x and x plus dx. We assume that the sound waves propagate towards the right of the screen, aligning it with the positive direction of the x-axis. Next, put up two circular surfaces of area S at the 2 points. The cylindrical volume of the medium trapped between these two surfaces can be thought to be a fluid parcel. We would study the dynamics of the material contained with a volume S delta x due to the passage of an acoustic wave through the medium and try to arrive at its equation of motion. We would select the longitudinal displacement of the fluid particles at each point in space as the dynamical variable. This variable is labeled SII and it is a function of x and t. The red circles in the diagram are displaced from the black circles by the amounts psi x and psi x plus dx at the 2 points at the time t. The mass of the parcel stays constant, and the only way that can happen if the density and hence the pressure inside the parcel changes. Expressing the condition that the mass of the fluid parcel is the same before and after the passage of the waves, we arrive an equation relating the excess density to the space rate of change of psi x at a given moment t. The quantity in the parenthesis in the first line of the equation is the change in the height of the cylinder. After the passage of the wave, the parcel boundary at the point x moves to x plus psi, whereas the point at x plus dx moves to x and dx and psi of x plus delta x. Note that we use different symbols to denote the distance between the faces and the displacement at each face of the parcel. We expand out the products and cancel whatever is possible. In addition, we also neglect the product of rho e del psi del x, since this would be way smaller than the other product rho naught del psi del x. This leads to the relation that the excess density is proportional to the negative gradient of psi. The negative sign makes sense, as when the derivative is negative the parcel shrinks and the density increases. Next we analyze the forces acting on the two faces of the cylinder. The forces are due to the pressure of the rest of the fluid acting on the parcel. The force OS proportional to the gradient of the pressure field. This makes perfect sense, as when the gradient is positive the pressure is more for more positive values of x, and therefore, the rest of the fluid exerts a net force towards the left on the parcel. It is perhaps easier to remember that the volume force I.E, the force per unit volume, EFFX by capital S delta x, is just the negative gradient of the hydrostatic pressure field. We have formed the RHS of Newton's second law. We have to equate it to the rate of change of momentum of the parcel in response to the pressure force. The rate of change of momentum is the mass of the parcel times the particle acceleration d2 psi dt2. Equate, cancel the factors of s and delta x from both sides and arrive at an equation relating the particle acceleration to the gradient of the excess pressure field. The excess pressure field is proportional to the excess density, so we have the gradient of the excess density on the RHS now. Now invoke the relation between the excess density and the ambient density. Since this relation contains the negative slope of the longitudinal displacement, one arrives at a certain proportionality between the second derivatives of time and second derivative of space, with the proportionality constant key being the slope of the EOS at the original density. Newton's laws, applied to a fluid parcel, therefore leads to the form of the wave equation. This implies, for one thing, that the longitudinal displacements would indeed behave like waves and that the speed of the wave would be the square root of the constant key. Next we see that for isothermal processes the constant is simply the ratio of the unmodified pressure to the original density of the medium. The speed of sound, being given by the square root of this ratio, you should be able to calculate it given what you know about atmospheric pressure and densities, turns out to be 298 meters per second and is known as the Newton's value for the speed of sound. The value is smaller than the experimentally observed value. The correct speed of sound can be obtained by assuming that the formation of sound waves is a fast process during which heat neither enters nor leaves the individual fluid parcels. The calculation shown in the slide shows that in this case the sound speed would increase by a factor of sqrt gamma. Make use of the fact that air is mostly composed of diatomic molecules to show that the speed of sound in air now becomes 343 meters per second.